In this example, we're going to look at the case of an object sliding along a horizontal plane. This might be the case of, for example, a hockey puck that's been struck along the ice and is now moving with some velocity, and it's being acted on by the force of friction. Friction always acts in a direction opposing the motion. So let's draw in the force vectors. So there's our force of friction, here's our velocity vector. Let's say this thing has a mass m. Its weight, as always, acts directly down. Fg equals mg. And the ice pushes back up in the opposite direction with the normal force, the contact force between the two surfaces. So what else? We've got any other information. The object's moving at initial speed. It's being pushed by the force of friction in a direction opposite to its direction of motion, so it must be slowing down. So we'll indicate that by an acceleration vector with that direction, and we'll define a coordinate system such that the positive x direction is that way. It's always helpful to define your coordinate system such that the positive direction is the direction of motion. So now we're going to apply Newton's laws to see if we can derive the equation of motion for this hockey puck. So Newton's laws, of course, proceed by thinking about the net force. So the first law says that if there is zero net force, the object's velocity will remain constant, or if there is a net force, there will be an acceleration. So we know that there will be an acceleration because, as we can see here, in the x direction, there is a net force. So let's write then our expression for F net. Now, there is only one force that we can see, which is the force of friction, and it's in the negative direction. So I'm going to put minus F friction. Now, Newton's second law, of course, tells us that F equals ma. So in other words, the net force equals the mass of the object times the actual acceleration that the object experiences. So let's replace F net with ma. Now on the right hand side, we can put down a usual expression for the force of friction, mu Fn. Now which coefficient of friction is this? It's moving, so it's the kinetic friction coefficient. Now we can replace our Fn, of course, minus mu k with mg, because the normal force in this case is equal and opposite to the force of gravity, or the weight. So there we can write our expression. And now we can solve for a, the acceleration. We see that the mass cancels out, so this equation apparently applies for any object sliding along in response to the force of friction. So there's our acceleration. And now we can find the velocity of the object at any time. V equals v naught, the initial velocity, whatever that might be, minus at, or in this case, mu, oops, got my mu the wrong way around, mu k g times t. Meanwhile, what about the displacement? Where is this object at any particular time? Well, it's at its initial position, plus v naught t minus 1/2 mu k g t squared.